Bet I've read more books than you. I've read 10.
And I've read 50.
Oh yeah? Well, I've read Infinity.
I've read Infinity plus 50.
And wait, that's not more.
As children, we faintly understood that infinity is the biggest number and we can't have anything more. However, we never grasped what it really is or how it works. In this video, we will review some attributes of infinity and how some infinities are bigger than others. To start with, infinity isn't even a number, it's a type of number. In our introduction, when little Sally added 50 to her set, Johnny was quick to point out that it didn't make it more. Infinity plus 50 is still infinity. Hard to imagine? Well, we don't have a problem saying a positive number plus 1 is still positive. But before getting into it, let us do a brief review of some terms from set theory. A set is a group of things. This is a set of 4 dogs, and this is a set of 3 apples. The number of things or elements in a set is called its cardinality. 3 is the cardinality of this set of forks. When sets have the same cardinality, they are considered the same. When it's not practical to count, we can use a technique called a bijection to pair all the elements from one set with the elements from another set so that they line up 1 to 1. For example, if the hotel receptionist tells us that all rooms have been taken by single travelers, then we know that the number of guests is equal to the number of rooms in the hotel. No counting needed. There is a bijection or pairing between the rooms and the guests. We can describe the quantity of guests checked in with cardinal numbers, like 1, 2, 3, but to convey the order that they checked in, we use ordinal numbers, like first, second, third, and so on. The order of elements in a set is its ordinality. So far, we've seen an example of a finite bijection, but let's look at a set with infinite cardinality. To help illustrate this characteristic of infinity, a German mathematician of the 19th and 20th century named David Hilbert created a thought experiment known as Hilbert's infinity hotel paradox. He described a hotel with an infinite amount of rooms, each being numbered starting at 1, then 2, 3, and so on forever. One busy night, when the hotel was completely full, a man walked in looking for a room. The manager still accommodated the new guest by simply moving every current guest to the next room over. The guest in room 1 moved to 2, the guest in room 2 moved to 3, and so on. Since there was an infinite amount of rooms, there was no issue. Infinity plus 1, or plus any finite number, equals the same infinity. The first smallest infinity is Aleph Null. It is the set of natural numbers starting with 1 and increasing by 1 forever, like the preceding room numbers. Now, your intuition may imply that there must be twice as many natural numbers, which includes both evens and odds, as opposed to just evens or just odds. But both sets have the same cardinality, Aleph Null. To illustrate this, we can match each natural number to a room labeled twice the value, and we have another bijection. We won't run out of rooms because we have an infinite amount of them. Bijections can also show us that the amount of natural numbers, integers, and rationals, that is, positives, negatives, and fractions, are also the same size. Now, what if the hotel manager did not want to disturb the earlier guests? He could have assigned the arriving guest to the next room according to the order of the check-in. However, the new guest would have to walk forever without ever reaching his room. He may not be able to count past an infinite amount of rooms, but if his is after those, then he knows he can order them. He needs ordinal numbers. Instead of labeling rooms 1, 2, 3, he can label first, second, and so on. And if he labels Aleph Nullth room Omega, then he can assign Omega plus 1 to the new guest. But remember, we've already shown that checking in a new guest after an Aleph null amount still leaves with an Aleph null amount of guests. So omega plus 1 is not bigger than omega, it just comes after omega. By the way, if your graduating class rank is omega, it means that there were an infinite amount of students that did better than you. So, is there a bigger kind of infinity that can't fit in Hilbert's hotel? Well, yes. George Cantor, the 19th century German mathematician that also created set theory, proved that the set of real numbers is more numerous than the set of natural numbers. Real numbers are all the possible numbers on the number line. They include irrationals, the values with endless digits like the square root of 2 and pi. Want to see the proof? So far, we have shown that the amount of natural numbers is countable. Even if it takes longer than we will live, we can start with 1, and the jump between each one is finite. However, if we go with real numbers, where would we even start? Let's see. We can start with 1. Oh wait, here's a half. Oh, we missed a quarter. Let's try another way. We'll just use Cantor's diagonal argument. Just imagine we can list all the real numbers. We're talking amount, so they don't have to be in order. Let's just randomly list them without repeating them. If we can match a whole number to every number on the list, then they are the same size. But if we can always continue to make a new number that is not on the list, then the reals are uncountable. Now we select digits in a diagonal fashion and add 1 to each. For example, the first decimal digit of the first number plus 1, the second digit of the second number plus 1, and so on. Our new number is different from every other number on our endless list in at least one place. So we have found a number that is not on the original list. Since we can keep repeating the process, our list is never complete. The total amount of real numbers is uncountable. The size of the set of real numbers is called Aleph 1, or the infinity of the continuum. Interestingly, the amount of points in an interval is also a continuum. Yes, the intervals or gaps on the number line, such as between 0 and 1, contain as many numbers as there are numbers on the entire endless number line. Intuitively, we tend to think that the interval between 0 and 2 has twice as many points as the interval from 0 to 1, but amazingly, all intervals have the same cardinality. They are all as big as the real numbers. To demonstrate this, we can bend an interval into a semicircle and project a ray out from its center. Every point on the interval can be projected to a point on the number line. Every point has a buddy, so it's a bijection. But how do infinities apply to the real world? In physics, an infinite amount of real photons, the particles of light, are emitted and absorbed by any and every accelerated electrical charge. Infinity also shows up in the analysis of black holes and their event horizon. And in computer programming, by design, some algorithmic procedures go on indefinitely. This can be handy to know when writing code. And closer to home, we all enjoy the benefits of the invention of the wheel, and we can argue that a circle is just a polygon with an infinite amount of sides. But in the end, it's a philosophical debate as to whether or not infinity truly reflects the deeper truth of reality, or is it merely an artifact of our mathematical models?